Yes.
Okay. Is it on now?
Yes.
We are continuing with chapter 3. I think we left off on page 51. We need to learn how the oceans move and about waves and tides. That's what we're going to be studying today. Hey, what's that called?
Sushi disc.
A little Sechi disc. Who's doing their first reading today? Stephanie. Exciting. We're going to get some readings done. Learn about our island waters. Isn't that exciting? Okay. All right, so we learned a lot of stuff about ocean currents. In the northern hemisphere, ocean currents move in a large clockwise circle around the entire ocean. In the southern hemisphere, it goes in a counterclockwise direction. Do y'all remember why that is?
Because of the Coriolis.
Because of the Coriolis effect. In the northern hemisphere, everything turns to the right. Turns to the right. And in the southern hemisphere, everything turns to the left. And that's the Coriolis effect. We learned that last time. So here, next to our coast, we have the Gulf Stream. If you go far enough offshore, you go to the Gulf Stream. Have you ever been to the Gulf Stream before, Trey?
Yep.
How far out is it?
About 80 miles.
80 miles? How long does that take in a boat?
2 hours, 2.5
Couple hours? Some big fish out there, though, aren't there? What's the biggest one you ever caught?
Caught? I don't know how big he was when we got him in, but we saw 15-foot tiger sharks from the side of the boat.
Wow. It's big. Tiger, 15-footer. You know how you know that when you're in the water, Chief? You can tell by looking from the dorsal to the tail. What movie?
Jaws.
It's Jaws. That's one of our movies. You can rent it from me and watch it and take the quiz and get extra credit.
Did you dress up like him in
That's right. Last year I was Quint. That's one of my favorite movies. Now, a little note on the Gulf Stream. The Gulf Stream moves from south to north, so it brings warm water in from near the equator, way down here on the coast of South America. Warm water will come in, warmed by the sun at the equator. And so we get nice warm water. So you go out and swim in the Atlantic Ocean, it's nice and warm. The opposite is true in California because of the current. Cold water from around Alaska is brought down into the coast of California. So that water's always cold. It never gets warm. Most of the surfers and stuff that are out there on California coast wear wetsuits because the water's just so cold. If you stay in it that long, you'll get hypothermia. Hypothermia is the condition when your body gets too cold. By the way, they have real big waves on the west coast, and we have small waves on the east coast. Do you know why? We already talked about it.
Because of the active and passive stuff.
Active and passive margins. Down there on the west coast, there's a plate diving underneath this continental plate. There's a separation of plates right there. So you get real deep water, deep trenches. When one plate goes under another, it kind of drags downward, and you have this deep trenches. So there's real deep water right off the coast of California. And deep water means big waves.
And big sharks.
And big sharks, too, big fish, too. So there's deep water right there on the coast of California. Here, we're at a passive margin. There's no plate diving under another one. So we have this real shallow water coming off of our continent for a long ways, and that makes the waves, by the time they come from the deep water in the middle of the Atlantic to where we are, they've gone through 80 miles of shallow water, and they've gotten smaller. So we don't get big waves over here. And you have to go a long ways offshore to get to the deep water where the big fish are. So there's some differences there. But we have the warm water, and they have to deal with the cold water. So anyway, that's just some interesting stuff. Another thing that you might want to note is the Gulf Stream. Probably better if I draw this. The Gulf Stream, and you might want to, yeah, very good. You're good. Good camera person here. Might want to consider doing that as a job. The Gulf Stream goes up like this and brings the water upward. And there's little eddies. Do you know what an eddy is? You can kind of see it if you run your hand through the water like this. Little water kind of swirls this way off of that current. And it does it on both sides. And so the Gulf Stream's coming up like this, but there's swirls, little eddy currents coming backwards. And so where we are on the coast of Georgia here, there's Florida down here.
Eddy swirl?
Yeah, it's called an eddy, E-D-D-Y. An eddy current. So actually, if you're standing on the coast of St. Simons, here's St. Simons right here. If you're standing on the beach down here, the current will take you this way, in this direction. I don't know if you've ever noticed that when you're out there just floating around on a raft or something like that. You'll go down the beach to the south, not up the beach to the north. Does anyone ever notice that? You've noticed that?
I always thought it was the opposite way.
No, you'll go that way. We have a name for this current that pushes everything to the south. It's called a longshore current. Longshore current. And it runs this way. It's always kind of going this way because of these eddies that come off the Gulf Stream. Pushes sand and stuff down too. So the sand from the islands actually moves. The sand is slowly moving over months and years in this direction. It comes down from rivers. Rivers will dump it out. The Savannah River will dump out sand, and then the sand kind of moves this way. It's kind of interesting. The north side of the island tends to erode sand that moves down towards the south side of the island. The south side of the islands tend to build up sand. And islands will actually grow. The south end of islands will actually grow in a southward direction because the sand that's deposited on them, the north kind of erodes and the south grows. And the islands themselves move as the north side of the island erodes, and the south side of the island grows. The whole island moves like this to the south over hundreds or thousands of years. Isn't that cool? We've kind of stopped that process by digging channels in between the islands. So the south side of the islands are no longer allowed to grow because we've dug a channel in there, and the sand falls into the channel instead of building the south end of the island.
Is that like dredging?
Dredging. Mm-hmm. So human influence has stopped the movement of these islands.
There's like an island around here that's made of dredged
Yeah,
sand.
yeah, they got to put it somewhere. And I don't know if you've ever noticed this. I'll show you when we're riding along. Have you ever been riding along and over in the marsh you see an island? Like a place that has trees and bushes and stuff that kind of sticks above the marsh? Most of those are man-made islands of stuff that was put there. And it raised the level so plants could grow on it. Kind of interesting stuff. They're called ballast islands. We'll talk more about that later. This is just a chart showing the temperatures around the globe of the ocean. And you can see the green, cooler temperatures kind of spread southward. And the pink, warmer temperature kind of spreads northward. because of those currents. And of course, it's just the opposite in the South Pole. As a matter of fact, when I went to the Galapagos Islands a few years ago, which are right there, see those little islands there? Those are the Galapagos. That water there is cold. It's a lot colder than the water here on the coast of Georgia. And I didn't think that that was going to be the case because that's on the equator. That's the equator right there. And I thought, I'm going to an island that's on the equator. It'll have warm water. But you almost have to wear a wetsuit there because of this current bringing the cold water northward. And there are actually penguins on those islands that came up a long time ago from the Arctic, followed the cold water up, and it's the northernmost location of penguins in the world. They're called Galapagos penguins. Isn't that cool? I'll show you all those slides of the Galapagos later. Very interesting area. So if you measure different things about the water, about the ocean at different depths, we already talked about the temperature. The temperature is real cold in the ocean until you get at a depth of less than 1,000 meters. Then the temperature goes up. And do you remember what we call that rise in temperature from 1,000 meters up? There's a name for it. As the temperature goes up, as you get shallower than 1,000 meters. Do y'all remember that? The thermocline. Very good, yeah. Thermocline. It's written right there for you. You could have just read it out. Did you read it out, Vanessa, or did you remember? You read it. That's okay.
Wait, can you say definition?
Check this line. Look up here, this line. You see how the temperature goes up? Here's the temperature up here. Temperature goes up as you get shallower than 1,000 meters. That's the thermocline. The rise in temperature as you get shallower than 1,000 meters. This water is real cold down here. Almost freezing. Deep water cold. A couple other things you should know. The salinity of the water is pretty much 35 parts per thousand, deeper than 1,000 meters. But it can vary at the surface. All the way from 33 parts per thousand, all the way up to 37 parts per thousand, depending on where you are. Generally, if you're in an area that's real hot, the ocean will evaporate. The water will evaporate and leave the salt there at the surface. So if you're in a real hot area, all this evaporation of the water leaves the water saltier. So it gets up to 37 or so in real hot areas. And just the opposite of that, it gets less salinity in areas that are colder. Because the opposite process is happening. You're not getting as much evaporation.
So there's more salinity.
Generally, there's more salinity in a real hot area. Now something else can change that. What else could change the salinity of the surface water? Y'all are smart. Y'all can figure this out on your own. Mixing could change it. Yeah, mixing below. But something more obvious than that. Rain. Yeah. If you're in an area where it rains a lot, you're going to have more or less salinity, do you think, of the water on the surface? Less. This is all makes sense if you think about it. One other factor is freezing. If the air gets so cold that it freezes the ocean, only the water freezes. The salt doesn't freeze. So a glacier is all fresh water, even if it's floating around in the ocean. Because the water will freeze and the salt won't. So the water around where glaciers are contains a whole lot of salt. Because the water is freezing into ice and the salt is left. So it's real salty around glaciers. around ice, floating glaciers. So icebergs, I guess is what we call them. So there's a lot of salt too in real cold areas, as well as real hot. Trey, this isn't fantastic? This shows the density of water and in grams per cubic centimeter, and the density of water will go up as you get deeper. And a lot of that is due to temperature. The colder the water is, the more the molecules kind of come closer together because they're not moving so fast, so they can kind of bunch together and you get a little bit denser water.
Density of anything to do with pressure? Like does pressure like increase density at all?
Yeah, the pressure will be higher the denser the water is, slightly. Here's a couple more graphs talking about temperature. Obviously, if the temperature of the air is hotter, the surface temperature of the water will be higher. So they got three lines here showing what it's like in polar regions, what it's like in temperate regions, and what it's like in tropical regions. Because there's different air temperatures, you see. If the air temperature is real cold, the surface water temperature is not going to be high. It's going to be about the same as the air. But if the air temperature is really hot, like in the tropics, that'll bring the surface water temperature way up.
Why are some lakes like freezing cold even if they're like in really hot areas?
Well, the lakes have what's called a stratification, similar to what the ocean has. The surface will be affected by the air above it. But as you go down, the temperature will change. It's not near the surface. And colder water is heavier, so the colder water tends to sink. And warm water stays on the top, so you have these layers where it gets colder as you go deeper. And the only thing that'll turn that over, that'll mix it back up, is when the air gets real cold. So that the surface water, as it gets colder, falls down, gets heavier, and falls down.
Have you ever heard of Lake Powell in Salt Lake City? It's like huge. It's really, 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 really
Cold.
It's freezing.
I don't know why, but Salt Lake City gets real cold in the winter. And if it's got a lot of salt in it, it won't freeze as easily also. That's another factor. But I don't know anything in particular about that lake. But let me move forward from here. So here's what ends up happening. Near Antarctica and near the North Pole, you have such cold temperatures that a lot of the water freezes and becomes ice and leaves the salt there at the surface. Are y'all following me here? Because this is kind of a little story to it. So at the poles you get these icebergs forming. The salt that's left in the water makes it real salty, and salt water is heavy. So the water that doesn't freeze falls. And that's what it's showing here. You have a falling of the water near Antarctica and near the North Pole. They both fall down. So the water, you have what's called a downwelling. Water near the poles falls to the bottom of the ocean rather quickly. And we're talking about a huge amount of water here. And this downwelling that happens at the poles drives what's called a conveyor system, the Great Ocean Conveyor, which you probably didn't even know existed. the Great Ocean Conveyor. Due to the water sinking and spreading through the oceans. And I'll come back, let me come back to this bit of notes. But water, when it reaches, let's just deal with this water here near the North Pole. It gets cold, and a lot of the water freezes and becomes icebergs, and bam, that water sinks to the very bottom. And it flows along the bottom of the ocean, very slowly, down at the bottom of the ocean, and follows this path. So there's a current at the bottom of the ocean that moves the water. It ends up going all the way around the world. It ends up finally getting warmer and rising back up to the top. And so there's a current that runs at the top and then ends up falling back down. And this is a huge current. It's called the Great Ocean Conveyor. The deep circulation of the ocean is part of a global pattern known as the Great Ocean Conveyor. This circulation constantly replenishes the oxygen supply to the ocean depths. Small variations in the conveyor circulation are thought to produce dramatic changes in weather patterns around the world. Large changes may even bring on ice ages. Did y'all ever watch the movie The Day After?
Tomorrow?
The Day After Tomorrow? Yeah. That was about this. And let me tell you the premise of that movie. They only talked about it for like a minute. You may have missed it. The movie was decent. It wasn't that great. It had good effects. I like the guy that froze in the helicopter. Y'all remember him? That was my favorite part. What happened was, due to global warming, Trey, are you following this?
Mm-hmm.
Lift your head up so I know you're following this. Did you see the movie, Trey?
Absolutely.
Okay, you need to look at this. Due to global warming, the ice on Greenland started to melt and empty into this area here. And what that did was it diluted the salty water that was right here. This didn't really happen. This was in the movie, okay? But it is happening right now. This Greenland ice is melting. And all this fresh water is running here. And the only reason why the water is sinking down to the bottom is because it's so salty. So when you dilute this fresh water, this salt water, so it doesn't sink anymore, that means if the water there is not sinking, it shuts the whole conveyor off. Because if this water doesn't sink, it just stays on top here. And then the water behind it is not being pulled. See, when this water sinks, it pulls more water into the area. And if that whole sinking of the water stops, it quits pulling water up, and the whole conveyor turns off. And if this whole conveyor turns off, that means warm water is not moving over here toward England. And the whole place can get a lot colder because the warm water is not coming in. And it can cause England, here, Europe, to go into an ice age. And that is indeed what happened about 100,000 years ago. Europe went into an ice age because part of the all these glaciers in the, I'm sorry, it was about 10,000 years ago. There were a lot of glaciers covering North America, and all that water melted and ran in over here, and it stopped the conveyor. And Europe went into an ice age for about 1,000 years, just a real short little ice age, because that conveyor belt stopped. Yeah?
Do ice ages happen as fast as it did in that movie?
No. That was all made up. It wouldn't happen nearly that fast. It would happen over a period of maybe 10 or 20 years that it could get real cold. If this if this conveyor belt shut off. But 10 or 20 years is real fast compared to the age of the Earth. So it is happening fast, but not in one day like it happened in the movie. Okay, here's waves. Do you know all the parts of the waves? We're going to talk about waves next. Do y'all know the parts of a wave? Did you learn this in physics? The crest is the top of a wave. The trough is the bottom of the wave. The wave height is from trough to crest. A lot of people don't know that. A lot of people think the wave height is from the middle of the wave to the top. It's from the very bottom of the trough to the very top of the crest. That's the wave height. They'll say that on weather reports. Do you listen to them before you go out on your boat? Waves are 2 to 3 feet. Waves are 6 to 8 feet. They're talking about from bottom to top. Which is a lot when you're going around in a boat and every time a wave comes by, your boat's falling 6 or 8 feet. This is a 10-foot ceiling. If you're out there in 10-foot waves, that means every wave that comes by, your boat's falling that far. When you're in waves like that, it can feel like a roller coaster. I mean, you're going way up, down, pretty quick. It can get dangerous. If the seas are too high, it'll flip your boat over. Did y'all see the movie, another movie, A Perfect Storm?
Yes.
That's a good movie. There's these huge ocean waves that came about because this big storm, a couple of storms hit in the same place at the same time. Formed these huge ocean waves that'll sink ships. That really did happen. A ship went down because of the huge waves. It flipped the ship right over. Look at the little bird. Why is it sitting there? They show a bird sitting there because they talk about in the reading the bird. As the wave comes by, the bird just goes up and down. The bird isn't pushed along by the wave. Waves are energy passing, and so the bird kind of just bobs up and down. It actually goes, the bird will go in a little circle, which I'll show you in a second. The wave here is moving from left to right, and the distance between two wave crests or two wave troughs, we call that the wavelength. Wavelength. And in this picture, the wavelength is at a certain distance here. I don't know, they aren't showing us the measurement of the wavelength. They're telling us that a wave takes 15 seconds to get from one wave to the next. And that's a measurement of the frequency of the wave. The frequency of that wave is related to this number here, 15. The frequency is not 15 seconds, but it's 1 over 15 seconds. Is how many waves pass per second is typically the frequency. Hertz, you may have heard of that before. And we're getting a lot less than 1 wave per second. We're getting 1/15th of a wave per second. So that's called the frequency. And here you can kind of see the movement of the water particles as a crest goes by. The water particles kind of move forward. And then when the trough comes, the water particles move backward. So this bird, as it's floating around in the ocean, would actually make a little circle as the wave comes by. It would be sitting here, and here comes a wave. It goes forward a little bit, and then here comes a trough. It goes back a little bit and comes back to the same point. So the little floating bird would go woo, woo, as the wave comes by. And we just sitting here doing these little loops if you were to watch the bird sitting in the ocean. It would never leave its position, though, as these waves go by. The only time you actually move forward by a wave is when the wave is breaking near the shore. That's why surfers can be propelled along. But that only happens as a wave breaks. And the top part of the wave starts to move in front of the bottom part of the wave. That's called a breaking wave. Mm-hmm. You might miss the tsunami video. Waves are made by the wind. As the wind blows on the water, it'll blow up a small wave. And a wave acts like a sail. A wave actually will easily capture more wind because it has a surface to it, like a sail has a surface. So once a small wave is raised, the blowing wind will continue to make it larger. And the wave will get larger the longer it goes. So you can see the waves, the wind is blowing this way. The waves over here that are crashing on this shore are bigger than the waves over here that are crashing on this shore, because this area is shorter than that area. And the wind has had longer to blow on this wave than it has to blow on this wave. You see what I'm saying? We call the distance through which the wind is blowing over the wave, we call that the fetch. F-E-T-C-H. The fetch. That's a good boating term. Trey, did you know that one? So there's a greater fetch right here than there is right here. Thus you have bigger waves right here than you do here. Does that make sense? Now the waves will get smaller if the wind stops blowing or if the wind changes direction. So you only get real big waves when the wind is consistent over a long period of time and over a long fetch. Yeah. You got to go too? So here we see the wind blowing, causing some waves. And what happens when the waves get near the shore starts coming up here and the waves will crash. What happens is the bottom of the ocean slows down the bottom of the wave. Imagine I'm a wave and I'm moving that way. La la la, I'm just a wave and I'm moving that way. And then all of a sudden, I raise the bottom here and it slows down my feet. What's going to happen to me if my feet suddenly slow down? I'm going to topple. That's exactly what a wave does. When the bottom comes up like that, it gets in the way of the bottom of the wave. The wave is a large structure there, and when the bottom comes up, slows down the bottom of the wave, and the top crashes. That's what happens near the shore, the top crashing. And when the top crashes, there is energy now moving that way. And any particle that's in front of that crashing wave will be moved that way. And sand in the ocean will be pulled that way, and a surfer will be pulled that way. And if you're riding one of those tubes or whatever, you can be pulled that way. It's fun. Unless the wave's big enough. And it hurts. My sister's a pretty good surfer. She lives out on the West Coast. That brings us to tsunamis. Have you ever heard of a tsunami? It's also known as a tidal wave. A big wave that's usually caused not by the wind, but by a huge movement of one of the plates. When one of the plates shifts quickly, it'll push a lot of water. And if you put your hands together, everybody put their hands together and push kind of hard. Push hard where your hands are going together. Now, I don't care, are you doing this? You're not doing it. Look at me. Up here. Push your hands together. Okay. And you push hard, and then you slide your hands this way so they slip. They suddenly slip. If you get a sudden slip of a plate, and there's some ocean there next to it, and a plate suddenly jerks or slips, it'll push a whole lot of water at once. A whole lot of water. You can also get it if there's a landslide. If there's an earthquake and a mountain slides into the ocean, it'll push a lot of water at once. And you'll get a huge wave. and that's a tsunami. The tsunamis usually occur where plates come together. And there was a huge tsunami recently. Do y'all remember the one in Japan? There's a huge tsunami in Japan, and then a few years ago there was a big one out here in the Indian Ocean. This just shows the one in the Indian Ocean. It happened right here where these plates, one of them slipped, pushed a lot of water. In this case, it slipped above, one place slipped above another and pushed a lot of water out. And these waves travel real fast. They can go hundreds of miles per hour. You can't outrun them.
You can predict them like 6 hours ahead.
You can predict them?
Not predict them happening, but predict them coming.
Oh yeah, well, yeah, if the person on this island right here or in India says, we just got swamped by a huge tidal wave, then they can just call the people over here on the phone and say, well, if it's traveling at 500 miles an hour like most tsunamis do, it'll hit you in 5 hours. So that's how they predict. They feel it in one place and then they call everybody else. There are tsunami warning systems that are automatic. They can feel an earthquake anywhere and it will immediately call everyone else to tell them it's coming. But when this one happened in 2004, none of the Indian Ocean had a tsunami warning system. So nobody knew it was coming until it hit some of the nearby land areas. It killed 200,000 people. Hugely destructive. I got video footage of it. Crazy scary. It'll kill marine organisms too, not just people.
And when it is over, nothing is left. A tsunami. The word in Japanese means harbor wave. Japan has been hit by many tsunamis in its history as a result of its location. It lies across the edges of 4 tectonic plates, where most earthquakes, the principal cause of tsunamis, are born. When 2 tectonic plates push together, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. A series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed and raises their height until at landfall they can engulf a 10-story building. Unlike ordinary waves, a tsunami wave doesn't crest and break. Instead, it advances like a wall of water that crashes over the coastline and everything in its way, reaching even as far as a mile inland. More damage is caused when the wave recedes, dragging everything in it back underwater. And most tsunamis have multiple waves, each arriving anywhere from 10 to 60 minutes after the first strike, just when survivors think the danger is over. The deadliest tsunami ever recorded occurred in December of 2004. An earthquake off the coast of Indonesia triggered a tsunami that surged across the Indian Ocean and reached as far as the coast of Africa. Whole sections of cities were destroyed. More than 200,000 people died. Most most had no way of being warned. 5,000 miles away, the Pacific Tsunami Warning Center in Honolulu is on call 24 hours a day to prevent a similar tragedy from happening in the United States. Scientists monitor tremors and quakes from around the globe. If a quake big enough to cause a tsunami occurs, it is their job to alert the coastlines in the tsunami's path. The advice is simple. Move to higher ground, wait for news that the tsunami has passed, and be ready to deal with the ruins left in its wake.
Isn't 2004 the same year Katrina happened?
It might have been. It was pretty close to that
Katrina
time.
was 2005.
2005.
Here's one showing the one that hit Japan. This was more recent. It was a couple years ago.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next: run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesanuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall in the Kamaishi city. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing. When two tectonic plates push together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11. And a rare view from the air, video of a tsunami wave approaching the shoreline. In Japan, some tsunami waves reach as far as 3 miles inland. Japan may be the most seismologically studied country in the world, and with more than 1,200 high-precision GPS stations, a geophysicist at the University of Alaska used the data to create a visualization of the March 11 quake. The waves of displacement that you see were moving as fast as 5 miles per second. In this photo, the ripples of tsunami waves are seen moving upstream in the Naka River at Hitachi-Naka City. New technology left an enormous amount of visual evidence for study in years to come, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future.
It's not actually like a massive wave that crashes.
It's not like a huge tall wave. It's like just incoming water. And the waves are pretty tall. but the water just keeps rising and rising and rising. And it's hard enough to where, I mean, you couldn't swim or anything against it. It just takes you wherever. So if you get caught in it, you're pretty much dead, unless you get lucky and can climb up a lamp pole or something like that. Most people that get caught in it die. Okay, so that's the part about waves. The next section talks about tides, and we don't have much time here. Let me just basically tell you how tides work. The Earth has the moon rotating around it, or orbiting around it. And so the moon's got a lot of gravity, you see. And so wherever the moon is, the water is pulled toward the moon. So you get a bulge of water facing the moon. And as the world turns, that was an old name of a TV show. With the Earth turning like this water's bulged towards the moon, and as the Earth turns, this water's bulged towards the moon, and this water's bulged towards the moon, and so you get tides.
Is that high tide?
High tide is the bulge that's facing the moon. There's a similar bulge away from the moon too, on the other side. And you have to think about centrifugal force. Okay, come here real quick. I want to show you something. Grab my arms, I'm going to spin you. Put your hair back behind you. There you go. Watch your hair. I'm going to spin you around. Watch your hair in the back. See, it's going away from me? That was good. Good job. Do you see her hair going back? Imagine the Earth is like that, with the water on the other side going out. Because it's being pulled by the moon, just the way I was pulling her. So you got a bulge on both sides. You got a bulge going away on this side, that's a high tide, and the bulge going toward on this side. And as the Earth turns through those bulges, you have high tides. And when you're not facing the bulge, either of the bulges, you're at low tide. So high tide, low tide, high tide, low tide. 2 high tides a day, 2 low tides a day. Does that make sense? And that's what occurs in most places on the Earth. Now, because of all the continents and topography, and the water is going to hit the continents and shift a little bit and that sort of thing, you don't always have perfect 2 tides a day. Some areas are located in a weird spot where the bottom of the ocean is shaped funny and the continents are shaped funny, where you only get 1 high tide a day. But most places are 2 high tides a day because of these 2 big bulges. What a perfect ending I just